Myself, Dr. Sushma Jain, Associate Professor Chemistry, Government Dungar College, Bikaner. Today, I shall discuss about ring synthesis in organic chemistry. Ring formation have importance in the retrosynthetic analysis. In the retrosynthetic analysis, the ring formation is very favorable in the intramolecular reaction rather than intermolecular reaction, because in intramolecular reaction only one molecule is required for the ring formation or ring synthesis, but in intermolecular reaction two molecules are required for the formation of the ring. Here in the open chain structure, the molecule contain two end, one end is nucleophile and another end is electrophile. The nucleophilic end donate electron to the electrophilic end which accept the electron. So by accepting the electron from one end of the molecule, from the another end of the molecule, same molecule, the covalent bond is formed between this nucleophilic end and the electrophilic end, and the ring formation is possible. So the three-membered ring formation is illustrated here. In this way, the five-membered ring formation can also be carried out. The five-membered ring is formed very easily because the natural thermal motions of the carbon atom, which are in the form of nucleophilic end and the electrophilic end, and these nucleophilic end and electrophilic end forms a covalent bond. 3, 5 and 6 membered rings form rings easily formed. Here the diagram illustrates the formation of the three-membered ring. Both electron donor and electron acceptor should be nearer to each other. So three-membered ring forms very easily. In case of six-membered ring, here the six-membered ring is not formed very easily, because in the formation of the six-membered ring the chain is needed rotation before bonding. So the six-membered ring not formed very easily, five-membered ring formed very easily, and three-membered ring formed very easily. But when the six-membered ring is formed, it is very stable due to the six-membered ring flipped and convert into the chair formation, which is the stable formation. The four and six-membered ring are formed with some difficulty. Here this is the open chain structure containing four carbon atom. One end has nucleophile and another end has electrophile. These chain structures convert into this type of the structure in which the nucleophilic end and the electrophilic end must come nearer to each other so that they form the covalent bond. More than six-membered ring formed very difficultly. In the 3, 4, 5, 6 membered ring, 3 and 4 membered rings are strained and less stable as compared to 5 and 6 membered ring. 3 membered ring forms easily and break easily, and 4 membered ring forms very difficultly and breaks very easily. There are some factors which govern the formation of the ring, that is the kinetic factors and the thermodynamic factor. The ring which contain 3 atoms, the kinetic factor is that this 3 membered ring forms very easily, but this 3 membered ring is unstable, so the thermodynamic stability is very poor in case of the 3 membered ring. In case of 4 membered ring, it can form very difficultly and it is unstable, or we can say the thermodynamic stability is very poor in case of the 4 membered ring. In case of 5-membered ring, the 5-membered ring is formed easily and it is the stable. It is not break very easily, so it is stable ring. And the 6-membered ring form easily and it is very much stable, because the 6-membered ring convert into their chair form. The chair form is the stable form, so the 6-membered ring is thermodynamically more stable. In case of 7-membered ring, the 7-membered ring is formed easily and it is stable. The synthesis of saturated heterocycles can be done by the ring formation. The heterocycles may be 3-membered ring, 4-membered ring, 5-membered ring, or 6-membered ring. The 3-membered heterocyclic compounds are formed very easily. The 3-membered heterocyclic compounds are oxyren, aziridine, and thyrene. The 3-membered ring, if contain the oxygen as a heteroatom, then it called oxyren. The 3-membered ring containing nitrogen as a heteroatom, it is called aziridine. And the 3-membered ring which contains sulfur as a heteroatom, it is called thyrene. So the 3-membered heterocyclic compound which are stable and which are not stable but saturated, because here the 3-membered ring is very strained ring, so it is not stable and it form very easily. Now we discuss the 3-membered heterocyclic ring formation and their retrosynthesis. The oxygen containing 3-membered ring disconnection and their synthesis. The 3-membered heterocyclic compound containing oxygen can also be called as epoxide. So we called oxyren as a epoxide. When we disconnect oxyren or epoxide, the alkene is formed. So the alkene is the starting material for the formation of the epoxide or oxyren. So when we carried out the synthesis of oxyren, the alkene takes as a starting material. Now here we illustrate the disconnection of oxyren. When the CO bond disconnect at once, so we write here on disconnection uh, um, 2CO, and after disconnection at once we obtain ethylenic compounds. Here it is for when we disconnect this oxygen we obtain ethylene. The reagent used in the synthesis of this oxygen, the M.Sc, it is called metachloro-parabenzoic acid. It is an insertion reaction in which two bonds form in a single step. The example of disconnection of this alkyl oxygen, the two CO bond disconnect at once, so we get this type of the alkene. Now when the synthesis is carried out, the alkene is takes as a starting material, so the reaction of this alkene with MPCBA, metachloro-perbenzoic acid, this type of the mechanism followed. Here this carbon forms a bond with oxygen and this oxygen forming a bond with this carbon atom. Here the oxygen form this hydrogen atom, so here one transition state is formed here, this type, and by the hydrolysis of this compound we easily get the epoxide or oxyren, which is the alkylated and the metachloro-perbenzoic acid. The another method for the retrosynthesis or the disconnection of the epoxide is that the only one CO bond is break Here the example, this is the target molecule. In this structure the CO bond is break, only one CO bond is break, and we get here the positive end at this carbon atom and the negative end this at this oxygen atom. So this is the nucleophile and this is the electrophile. This is the electrophilic end and this is the nucleophilic end. And for the generation of this synthone, we employed this synthetic equivalent. And on disconnection of this synthetic equivalent, or here the CC disconnection is takes place between this and this carbon atom, and we get two synthones. It is a negative synthone and it is the here it is the positive synthone. The negative synthone is employed, it is generated by the Grignard reagent. Here this is the structure of Grignard reagent, and the positive synthone is generated by the addition of the negative atom at the positive end. So we add the Cl at this positively charged carbon atom and get the synthetic equivalent. So this compound and this compound is the starting material for the synthesis of our target molecule. Now the synthesis of our this target molecule can be illustrated by this. Here this is the starting material which can be obtained by the disconnection of the target molecule. This, in this structure the oxygen is more electronegative than the carbon atom, so the bonding electron is displaced towards the oxygen atom, and this oxygen get negative charge and this carbon atom get positive charge. Here this carbon has negative charge, so this carbon and this carbon form a covalent bond, and MgCl form, which is the which Mg has the positive charge, so O minus react with Mg plus Cl, so O minus MgCl form bond here, and C minus form bond with this carbon atom. So we can write the structure in this way. On hydrolysis of this compound, we get the hydrolyzed product. This is the this one, and MgClOH is liberated here, and by the liberation of HCl from this compound we get the target molecule which is employed in the disconnection. So by the use of the disconnection we disconnect the molecule into smallest molecule, and by the synthesis the smallest molecule is used for the preparation of the target molecule. So the retrosynthetic analysis is very useful in the synthesis of heterocycles containing three-membered ring and containing oxygen as a heteroatom. Thank you.